number, right? Is there any way for a single number to be unsorted? Absolutely not. A single integer or whatever element is always sorted. N is the length, yeah. So for all of these, we just assume that the n is the length of the array. So we're going to inductively prove on the length of n, right? So if n is 1, then we have a single element and it's sorted. Okay. So what is the inductive step? Well, the inductive step is when we have n is greater than 1. So for any size that is greater than 1, essentially. And here what we can do is we can assume, so this is our assumption, inductive assumption, whatever you want to call it. We assume that sort is correct for any array, for an array of length less than n. Okay. So we can't assume that is correct for n, but we can assume that is correct for any array that has length less than n. And now we have to show that it's also true for n. So how does merge sort actually work? Well, let's look at the recursion here, just as a drawing in this case. Of course, you'd use words or whatever to explain this. What happens actually is we divide it into two equally sized pieces. So we have n over 2 here, and we have n over 2 here. And then we recursively call sort on these, right? And because we made the assumption that sort is correct for any array of length less than n, we know that this is less than n, it must be. Hence, when sorting these, we do get sorted arrays back, right? And then what happens next is, so we sort it, sort halves, and then we merge it, right? And this merge operation here, we can, according to the question, assume is correct. So you don't have to prove this at all. You could say that it always takes the smallest element first in the two arrays or whatever. Doesn't really matter because we assume it's correct. And then once you're done, you get a single sorted array because that's the output of merge, right? So if you have two sorted arrays and you merge them, you get one single sorted array. So this is also correct. So for any n, we can get a sorted array for any, basically for any array, right? Because we didn't even assume anything about the elements as long as they have an order. As long as they can be merged, basically. That's everything we assumed. And merged, we know, merge is already something that we know is true. Yes. Is there any questions to this? I'm just going to wait a bit. Meanwhile,
I have a question.
Oh, sure. Yeah.
So we're talking about n divided by 2, right?
Yes.
So in this case, for example, what if there is an unequal number of elements in this array?
Yes, so this is a very frequent question, and it actually really doesn't matter because, well, you can just do this, right? So ceiling and flooring. Well,
oh yeah, no, I'm speaking more in the sense that we have had a couple of examples where you have literal, like someone has
powers of 2, right?
Yeah.
Yeah, I mean, if you have 3 elements, what you do is you just divide it into one of size 2 and one of size 1. That's it.
Oh, cool.
So you just it just splits into one of them. And why does this still work? Well, because why is this still O of n log n? Well, because if we look at the sort of complexity of a problem, then we look at n if it's very large. And of course, the only difference that can be between these two is a size of 1. And we know that n in that case is much greater than 1, right?
Yeah.
So it doesn't really change the complexity. So that's a very small detail. Generally, off by 1 things in algorithms doesn't really matter unless you like write pseudocode or something. But for analyzing, it generally doesn't matter too much.
Okay.
Can you assume that sort is correct for a less than n? Yes, because this is how induction works. So we show that it's true for all base cases, and then we assume it's true for all cases less than our recursive step. Right? When doing induction with arrays, will our assumptions always be algorithm is correct for length of a less than n? No. But in this case, we have to prove it for all arrays, right? So any array. And that can be sort of reformulated into it has to work for an arbitrary sized array. And of course, you might also have to make assumptions on the actual elements, but that is handled by merge. So we don't have to do that here. Okay. I think that was all the questions to 4. So that's good. Let's go to 5.1. Okay, so here we have to give a single algorithm that determines if A has a 2-sum. Okay, so first of all, what is A? A is an array of size n, and it has integers, both positive and negative. I guess also 0, but that doesn't really matter. And here a 2-sum is if 2 entries in this array sum to 0. And there's also a question where we have to find a 3-sum. And this is basically if 3 elements in the array sums to 0. Now, this is a general problem called k-sum. It's generally used for complexity analysis and stuff. You don't really have to worry about that. It can also be used for geometry, sort of algorithms. Not really entirely sure. It's a bit, it doesn't really matter for this course. But let's look at the actual algorithms first. So 5.1, what exactly can we do there? Well, we have to get something that runs in n squared time. So the simplest algorithm is basically a brute force algorithm. Basically, we go through. Siri responded, nice. Go through all I and j, right? So basically all pairs. And oops. Then we test if ai plus aj oops, is equal to 0. And if it's 0, then it's a 2-sum. Very simple algorithm. And of course, because we go through all ij, this runs in n squared time because there are n minus 1. Well, there are n here and then n minus 1 here because we don't choose the same element twice. So it becomes something on the order of n squared. So I don't think there are any questions to that. Let's go to 5.2. Now we have to give an algorithm that finds whether or not A has a 2-sum in n log n time. And it says here in the hint, use a binary search. So what is exactly meant by that? Well, if we sort of rewrite this equation here, or this formula, whatever, we get that A of j must be equal to minus I A of I. Right? What exactly does this mean? This means that for any element in the array, there's exactly one other value that corresponds to a pair that sums to 0. So what we can do is we can sort A. Okay, we know an algorithm to this. You don't have to specify. Well, maybe use sort A using merge sort, for example, because then we also know the complexity. So that might also be important here because we are talking about complexity. So sort A using merge sort. You don't have to specifically say how merge sort works. Just use it as a black box, basically. And now we go through all I, and then we search for minus a of I. And of course, if we find this element here, then we have a two-sum. So how long does it take to sort it? It takes O n log n to sort. We know this because of how merge sort works. And how long does it take to go through all I? It takes exactly n time to go through all I. But every single time we go through an I, we also have to search, right? And it takes log n to search. So you get O n log n. And because these two are the exact same, we get O n log n as our overall complexity. Of course, it would be something like some constant times n log n plus some other constant times n log n. Doesn't really matter. We can omit constants from complexities. Why do we need to sort the array? Well, if we use a binary search, the array has to be sorted. So that is basically the sort of requirement to use binary search. So I can just write that here, binary. Because otherwise it would run in linear time, right? So because we use binary search, we can get it in log n time for a single search. Okay, any questions so far? Okay. Let's go to 5.3. So it's n log n plus the sorting, yes. But in this case, we use merge sort specifically, which has also a complexity of n log n. If you use something like quick sort, worst case will actually be n squared for quick sort. So in that case, it would be also n squared. But of course, quick sort in general can also be faster. It has a really good best case, but here we specifically said merge sort. Okay, so 5.3, it's very similar to 5.1, right? So in this case, we can just go through all triplets, I guess, of elements and check if they sum to 0. If any of them sum to 0, then we have a three-sum. And of course, a three-sum is something where three elements sum to 0. So I'm not going to solve that here. However, let's look at 5.4. Again, this is very similar to 5.2 here. Sorry, there's another question for 5.2. I thought n log n was the sorting time. Yes, n log n is the sorting time, but n log n is not only it cannot only be the time of sorting. In fact, a lot of algorithms actually run in n log n. For example, going through all I, we do that n times, and for each of these i's, we do a binary search, which takes exactly log n time, right? And so when we sort of sum all these together, we get n log n in the end. So both searching through with all I and sorting the array takes n log n. So you end up getting O n log n plus O n log n, right? So this here is for search, and this here is for sort, right? And then you get O n log n. You just get one of them because basically you can remove one of them because they are the same. Okay, I'm not going to go through that again. So in the next one here, basically we can do the exact same thing, except here we can say that a of k is equal to minus a of I minus a of j. And of course, just like before, we sort and search, right? And this one here we do for all I and j. And this one here, we just do once, right? So how long does this take? Well, we have n squared here. Oops. And searching again takes O log n time. I think I did quickly go through here. It's very similar to 5.1. I'm just going to talk about that afterwards. So here, it's going to take log n plus n squared, and sorting is just like before. It's going to take n log n, right? And when we sort of multiply these together, we get n squared log n. So now we take the sum of these. Which one of them dominates? Well, this one dominates, right? N squared log n is definitely larger than n log n. So we get O n squared log n. Someone asked me to go through 5.3. I'm not going to go through it. If you want more questions, I guess you can. Well, if you want an answer to it, you can go through it, I guess, next week, or ask Philip or something. It's very simple. Just go through all triplets. So basically 3 for loops, essentially, right? If you talk about the programming of it. Okay, let's go to exercise. Wait, no. First of all, 5.5, I'm not going to go through that because generally we don't go through double star algorithms. However, I definitely recommend that you do it. It's definitely something where you have to get a good idea and sort of work through with that. I can give you a small hint. So think about, just like before we had that n squared log n dominates our other part of the algorithm, right? Is there a way that you can sort of use that fact to create an algorithm that runs in n squared time? Don't know if that helps, but generally, like, what other possibilities do you still have that is below n squared? Because you can do all of those algorithms separately as well. Okay, so exercise number 6. And yes, you are correct, Marcus. Thank you for explaining that. Okay. 6.1. So in this case, we again have an array, this time of distinct integers. And the integer with rank k is the kth smallest integer among those integers, right? And we know that the median is basically the middle sort of element with basically rank n minus 1 over 2 floored. Okay. So exercise 6.1 says that we have to give an algorithm that, given a k, finds the integer with rank k in a in n log n time. Yes. So let's think about another way to sort of pose the question. Instead of saying that we find the kth smallest integer, let's say that we find sort of the integer with index k in a sorted version of a. So if we were to sort a, then the kth rank would of course be the kth index. So knowing that, we can solve exercise 6.1 very easily. So all we do is we sort a, and then we just return AFK. It might be AFK minus 1. I'm not entirely sure. It doesn't really matter. Again, off by 1 errors. Doesn't really matter. But yes, I think also it's a k minus 1 actually. So the first one would be the smallest element, I guess. Yes. So how much time does this take? Well, sorting, just like before, takes O and log n. And this over here takes constant time. Which one of these dominates? Sorting dominates, right? So this solution runs in O and log n time. Okay. Any questions so far? Okay. So next up here, we have question 6.2. And this is sort of the quick sort part of the question. So it explains there, a partitioning of A is a separation of A into 2 arrays, A low and A high, where everything in A low is less than the median, and everything in A high is, less than or equal to, and everything in A high is greater than all the integers. Well, no. Yeah, well, I guess, but greater than the median, basically. And we are assuming that we have an algorithm that can basically return the median in linear time. Now, what does that mean? That means that it runs in O of n time. So we can find the median in linear time, just like that. And now we are supposed to give an algorithm that can partition A into A low and A high. So let's look at what we are actually asked here. So if we look at the array, we sort of have the median here in the middle. Then we have A low over here and A high over here. And then we have the median here. Okay. Now, what is the property that we want to be true? We want everything in A low to be less than or equal to. We want anything in A high to be greater than the median. So we want all these sort of equalities to be true. So how can we do that in linear time? Well, we can find the median. So we find the median m. And then we go through all I, which is not equal to the median, because that's the middle element. And then if the element at that position is less than or equal to the element in the middle, basically the median, then we have that AI is in A low, right? This might not be the best way to write it, but that's how I'm going to write it. And else, we have that AI is in A high, right? So of course, if it's not in A low, then it must be greater, and then it's in A high. So let's look how much time this actually takes. We have O of n here, and then we have n number here, because we go through basically all elements, all I, right? Well, basically n minus 1. But again, off by 1 when doing complexity, it doesn't really matter. And then we have down here, this takes constant time to check this if statement, right? So what is the total time then? Well, it's O of n plus n times of 1, which is of course equal to O of n. Because this here is equal to O of n, this here is equal to O of n. So basically you get something like 2n. Again, constants can be omitted when doing complexity. So we have here that it runs in linear time. Someone is asking if we have to sort the array to find the median. And no, we do not have to do that, because the question specifically said that we get an algorithm. Basically, a black box is what you call it. We get an algorithm that we can just call to return the median. So finding the median here is just using that black box. And why is it called a black box? Well, it's called black box because you're not allowed to modify it. You're only allowed to sort of give it input, and then it does some magic crunching, and then you get an output. And the output, of course, here is the median, and there's no input. Okay. Any other questions? Okay. Let's go to 6.3 here. So now we have to actually sort of make the quicksort algorithm. So give an algorithm to sort A in n log n time using recursive partition. So basically we have to apply this algorithm here recursively. What does that mean? Well, first of all, when applying something recursively, we have to find the base case. So just like the merge sort, what is the base case of what is the base case of our algorithm? That is when n is equal to 1, right? So when n is 1, we know that we have sort of a sorted array. What's the best way to sort of write this? Okay, so let's say that we want to sort our array, right? Sort A and N. Well, the first thing we can do is if N is equal to 1, we can just immediately return. Okay, so that is step number 1. Step number 2 is find the median. I guess actually you can just say create partitioning, right? So we just use the algorithm that we had above, create partitioning. Basically, now we have A low and A high. And of course, we also have the median. So how does this actually look? Well, if we just look at the actual array here, we have exactly what we had before. So we have A low over here and A high. And then we have the median here in the middle. And this still holds, right? And then our third step is recursively sort A low and A high, right? Now, what will this give us? This will give us a new A low and a new A high, where everything to the left of this is sorted and everything to the right of this is also sorted. And because this sort of property holds where everything here is greater and everything here is less, because this is also sorted, then we know that the entire array must be sorted. And that's all the steps there is to it. So once we're done with this third step, we know that the array must be sorted. So that is our algorithm. Now, how much time does this actually take? Well, we know that partitioning takes exactly n time because that's what our algorithm did. And everything else here is pretty much constant time. Well, it is constant time, right? Because A low and A high are sort of already within the array. So we don't have to do anything particular when recursively sorting them. Of course, you could sort of like have index bounds and stuff. But that is sort of an implementation detail. So the only thing that really takes time is this right here. This takes O of n time. Recursively sorting, that is just a recursive call. It technically takes O of 1 time to actually call. Of course, the actual algorithm takes something different, right? So you can sort of do this A1 plus the time it takes for n over 2 twice, so 2 times that. And this if statement up here is constant time. So in total, let's just try to convince ourselves what time this actually takes. And I'm going to draw something called a recursion tree. And I don't know if you've seen that before, but it's pretty straightforward. What do you mean? Is it greater than or equal to? See? You mean down here? It is specifically greater than because that's what it said in the exercise, and also that is how our algorithm worked up here, right? So it's less than or equal to here, and here it's greater than just greater than. Theoretically, you could also do greater than or equal to, but then you have this problem where it's suddenly non-deterministic because some elements over here might also be able to be over here because the median is equal to a lot of integers in the center, right? So to ensure that it's deterministic, we have it just like this. Okay, so let's convince ourselves that this sorting algorithm is actually running in n log n time, just like we were supposed to, right? So I'm going to draw a recursion tree. The first step here takes this O of n time. In fact, every single step takes this amount of time. So we have O of n on the first layer, because we have to create the partitioning. And then we sort of split it in two. So we have A low and A high. And then we have n over 2 here. And we also have n over 2 here. Again, off by 1 doesn't matter because we're doing complexity analysis. And again, we are assuming that n is much greater than 1, right? So off by 1 doesn't really matter in the grand scheme of things. And then we split it again on these layers. And here we get that it takes n over 4 time. And then, of course, we also have sort of some more here. And then we have, again, n over 4 here. And then we might end up at the bottom. And at the bottom, we have the constant size 1, right? So that is where we just have one element, this here. And that takes constant time. So we're just going to have a bunch of these that take constant time. Now, how many of these are we actually going to have? We're going to have exactly n of these because every single element must be at some point the bottom layer, right? And we have exactly n elements. But let's just consider what is the height of this tree and how does that correspond to the running time? So up here we have a time on this layer of n. Here we also have a time of n because we have n halves plus n half. And then here we have 4, that is n over 4. So we also have time n. And here we have an n that is constant, right? So we have n of these. Now, what is the height of the tree? The height of the tree is log 2 of n. So we have log 2 of something that takes linear time. Now, how can we write that? We can basically write that we have log 2 of n times O of n. And that, of course, is equal to O of n log n, right? So this is exactly what we wanted to show. Again, I don't know if you've seen a recursion tree, but you're definitely going to see it at some point. And this is the basic idea. It was just to convince ourselves that this actually runs in n log n time. Another way to say it is that each layer takes linear time. How many times can you halve it? You can do that log n times, right? Basically the exact same as this. So yeah, that is exercise 6.3. Any questions? Okay, so 6.4. Again, I'm not really going to go through that. Mostly because we don't go through double star exercises. But again, I can give a hint. So think about exercise 6.1. In exercise 6.1, we sorted the entire array. And then we really only needed the position of one of the integers, right? So there's really no reason to sort of sort the entire array. So in 6.4, you can sort of think about, is there a way where you can still find the kth smallest integer without sorting the entire array? And can you do that in linear time? And the answer to that, of course, is yes. So think about this algorithm here and think about if you can change it. If there are no questions, I'm still going to stay here till 12, but if there are no questions, then you can assume that I'm done here. So thanks for listening.